doing much math, but yeah, let's just get started. Okay, so just like an overview for I'm not sure like how much people know about like physics in general, but like classical physics essentially deals with stuff on the range that we like see it every day, like all those classical problems that are like, oh, so and so throws a ball at like a speed of 10 miles an hour or whatever, like what's the parabola it's gonna make, like how far it's gonna go. That's like classical. And then when you move to like the quantum realm, everything changes basically. And the difference between something like general relativity and like quantum physics is that quantum physics deals with the very small like subatomic particles, like things you can't see, whereas general relativity is like deals with like massive bodies, like gravity, like stuff that like will like affect the reality more around it, if that makes sense. So that's just like, and they don't really correlate that well, like between the two. So they kind of like contradict each other almost, or so like that's kind of one of like the main questions in physics these days. But essentially, this is a periodic table. I'm sure you guys know from like high school chemistry. All of these atoms, they're made up of protons, neutrons, and electrons. And like the number on the table, that's like the little number at the top, tells you how many protons are in each atom. And another thing is with the number of protons, like that defines the element. So like they can have different numbers of neutrons, but the number of protons will always tell you what the element is. And this is like more like a chemistry perspective. And I also just wanted to show you guys what I'm more using. Like, can you guys see this? Can you see this?
Yes.
Okay, so this little like table here, for some reason it won't let me scroll. But this is like the table of the isotopes that like I'm using like in my studies and stuff. And it shows you like all the different possible isotopes where this is just like one of each. Like the atom, all these atoms have like different isotopes, like different numbers of neutrons. So like when you look up like each nucleus, like it'll tell you the half-life, which is how long it takes before half of the element disappears. Um, like so they all have like these different properties, which are based on the number of like nucleons that they have, essentially. So that's just like the a small intro to it. Let's see. So this is like a bit too complex, like mathematically, but just understanding how atoms are bonded together. So there's this equation called like the Bethe-Weisacker formula that basically tells you the binding energy of each like nucleus. And like the nucleus is just the protons and the neutrons, right? So there's no electrons in this. Also, if anybody has like any questions or is confused, like feel free to interrupt me at any time. Just letting you guys know. But so essentially like there's certain things that nature likes that determine how tightly like that nucleus is bound together. So some of them are that like nuclei like to have the same number of protons and neutrons. Like nature really loves symmetry. So when you see that in a nucleus, it means it's like going to be more tightly bonded together than other ones. And um all of these like nuclei basically they're almost like spherical based on like uh small factors, like all of these factors like surface area terms, like Coulomb repulsion from protons. So protons have a positive charge. And then when they're really condensed, they like create like a positive force barrier. So that's why it's hard to bring like two nuclei close to each other. Um, and like all of these like little things kind of tell you why some nuclei like work and some don't. And just like I don't know how familiar people are with like high school chemistry with like electrons and stuff, but if you know how like electrons will bond up based on like where they are in the periodic table, it's kind of similar to the shell structure of like the nucleus itself, um which is like It also has like certain structures or certain numbers, like I think like 2, 8, like they're like perfect numbers that the nucleus has to like maximize the binding energy. So when it has um a certain number of protons and neutrons and they're like really similar, like it'll be really tightly bonded. But bigger elements like uranium, for example, which is like known in culture, is gonna have like a lot more neutrons, so it's gonna be like more unstable, if that makes sense. Sorry. Okay, I was like, I missed the slide. But so this like picture is just basically showing you what a nucleus is. Like that's like the notation for elements on the periodic table. The Z is the proton number, the N is the neutron number, and A is like the atomic mass number. So since electrons are really, really small, we say that their mass is negligible. It's not technically zero, but for most calculations, you can say that it is zero. And that's essentially like what a nucleus is. A lot of my information, I guess, or sayings like come from stuff that my professors have told me over time. So my professor always told me that like nuclei are small, dense droplets that form the anchors that hold atoms together. So you can imagine them as like, well, they're like the thing that creates like matter, I guess, like from that kind of standpoint. And they're really, really, really tiny. So like and sorry, atoms are composed of like electrons and like this nucleus. So in a football field, like a nucleus is like the size of like a pin, like in a football field. If the football field is like the electrons. So it's a really, really dense, like concentrated ball of matter. We know that now that like atoms are mostly empty space. So there is this experiment back in the day. It's called like Rutherford's gold foil experiment. But essentially, he shot like atoms through a piece of gold foil. And some of them, like occasionally, most of them would go through, but some of them would reflect off. And basically, that's how scientists came to the conclusion that like the nucleus or the atom must have like a small concentrated like part in the middle, and then they're mostly empty space. So like that's how we came to that conclusion. Yeah, so they're really, really small, 10 to the negative ninth times smaller than a bacteria, which is like one cell. So and then they're really, really dense, like 1 billion metric tons packed into 1 teaspoon kind of density. So they're just really small and really dense. Um, they have really strong binding energy at close range. So like it's really hard to separate like nucleons from like the nucleus just like for nothing. And then they're also just like moving around all the time. One of the most important principles, I guess, in quantum mechanics is like the idea that a nucleus can only vibrate in specific nodes, which means that like there's only certain energies that it can have. So Planck's law, he had this equation E equals hv, which is the energy times the frequency times Planck's constant, which is like this just constant number. It like had to be like multiples of that number. Like basically you can't divide energy into like smaller amounts. Like they have to be like certain numbers. Like these are not the numbers, but if it's like, oh, like it can only be like 1, 2, like 3 or 4. Like it can't be like 1.1. Like it can't be like 2. Like it has to be like certain states. And then as you get to higher energies, the possible orbits get really, really close together. So at first you have like 1, 2, 3, 4, and then later you'll get like higher numbers like 100, 100.1, 100.2. Like they'll just get closer and closer together when you get to higher energies. But the main point from this is that like energy is quantized, so it can only appear in like specific intervals. Did that? Okay. So I'm not gonna really get into this too much, but this is just like so you know that like protons and neutrons are not like fundamental particles. So there's even smaller things that make them up. But at least like with nuclear physics, mostly with what I'm concerned with, like we're looking at protons and neutrons as like the building blocks of matter. At electrons are actually fundamental particles. So like they're not, to our knowledge, made up of smaller things. But like a proton is two up quarks and one down quark, and it's held together by gluons, which exchange like color force, and it has to be like red, green, and blue. Like all three have to be present to like hold them together. It's kind of like I myself like don't really fully understand a lot of that kind of stuff. That's like more particle physics, but I just wanted to like make clear that protons and neutrons are technically made up of like even smaller things. And this is what like modern particle physics is like about, like discovering the Higgs boson particle, like all those things. Like those are all elementary particles. Um, Quarks essentially, like up quarks and down quarks are like the main components of like everything pretty much that you like see. But like top quarks, down quarks, strange quarks, bottom quarks, whatever, leptons, like certain types of leptons, like you only see them in like high energy interactions. So they're not really like too relevant to like our scale. Like more like a collapsing neutron star or like just big high energy events. But yeah, and also the funny thing about elementary particles is like they can decay into each other. So when you have like these particles formed by like super high energy collisions or however, like they can decay back into, for example, an electron is like the most base lepton. It has like the smallest mass, but like a muon can decay into an electron. So like they might change into each other basically. But this is like more particle physics, and I mean it is quantum, but in our interpretation, we're not gonna get really into that. But yeah, so the double slit experiment basically is like one of the most important like thought experience of like quantum mechanics because it shows us that like light behaves like a wave and a particle. Like wave particle duality is like one of the most important like points of quantum physics. And I guess it's like very counterintuitive to think that something can behave like a particle and a wave. But I'm just going to go through this experiment and kind of explain how we figured that out. So basically, they're shooting electrons like through a slit, right? And when you shoot like a single particle, like imagine like a marble. So the one on the right, let's look at that picture first. So if you're shooting like a single particle, like a marble, right? It's just going to create like two slits or like two lines is like basically the pattern, like assuming you're shooting up and down, like you're just recording where like that marble is hitting. Um, so that's what you'd expect to get if like electrons, or technically is photons, but if electrons are particles. So in this scenario, like if electrons are particles, then they're just going to make like two lines when you shoot them through two slits, because that's what a particle would do. But actually, it's observed that when we shoot electrons through through both slits, they create this interference pattern that's on the left. And the next slide, I'll show you like a picture, better picture. I guess I'll go back. So if you imagine like an ocean wave, like coming in, hitting those two slits, and like these waves like spanning out, the interference pattern, like that's what you would get from shooting electrons like through those slits instead. If this is confusing, there's a really good video that I always like force people to watch who have like no background. It's called like Dr. Quantum Double Slit. If you look that up on YouTube, it's like just a goofy video that explains it really well. But anyway, like I'll do my best. But yeah. So when you see like the wave kind of pattern, that's what you're gonna get from shooting electrons through slits. So this left picture shows you like what you actually get. And they tried to do things like, oh, maybe if we only shoot the particles through one at a time, it'll make the two slits. But even if you do it one at a time, it still creates this interference pattern. So essentially, like the only way for that to happen is when you shoot an electron like through the slits, like they're both going through like a single electron. Um, it's both going through both slits at once, neither of the slits at all, and then one at a time, like in order to create that interference pattern. So it has to be interfering with itself, basically. And that's how we know that they have wave phenomena. But now, the freaky part of this is when they tried to observe it and try to actually just measure which slit the electrons were going through, the wave function collapsed. So basically, it looked like the picture on the right again when they tried, just because they tried to observe it. So it started behaving like a particle when like they were just trying to observe which slit it actually went through. So it's this concept of like observation collapses the wave function, where like when you observe like a quantum mechanical state, it like collapses into like one state. So that's like one of the big, I guess, paradoxes of like quantum physics that we still have to this day. But yeah, I think this experiment is just a really great like visual representation of like wave particle duality. But yeah, and just like if you just imagine like ocean waves, right? The way that they interfere with each other, it's like pretty similar. It's like the same kind of interference pattern that would be created. But yeah, so that's the double slit experiment. That's where we get wave particle duality. Um, so Heisenberg uncertainty, um, basically it tells you that you can never know the position and the momentum of a quantum object like at the same time. So I found this picture that I thought like did a good job illustrating it. So I guess I should say like before I keep going, like waves are like sine waves. Like imagine just like a sine wave, like oscillating. Like that's the kind of interpretation we have of waves in this sense. But for example, like this roller coaster, if you take like a snapshot of it, the picture on the left, like it tells you the exact position, right? But you don't really have any information about the speed. And the same thing with the picture on the right. Like you can see like it's in motion, like it's blurry, like it tells you something about the speed, but the position is uncertain. So Heisenberg uncertainty basically tells you that like you just can't know both of those things like at the same time. Like that's like one of the big ideas of like quantum mechanics, that like things are distributed, or like particles are distributed in time, like they're uncertain. And then this second, so this first equation that I've written is like position, is the uncertainty in position, which is x, and then the uncertainty in momentum has to be greater than this like Planck length, this like constant over 2. So it's just like the uncertainty has to be like a certain amount. There's always going to be a certain amount of uncertainty. And this next equation basically tells you that like a quantum state that only exists for a short time can't have like a definite amount of energy. So if you imagine it as like spectral lines where each line is like a certain energy, if it was a definite energy, it would just be like one very skinny straight line. But in reality, it's more like it has like some width to it. Like it has like some thickness to it because the energy is uncertain. So it can't, instead of being like one line, it's like more like a thicker line than a skinny line because yeah. But yeah, so that's like one of the most important things, I guess, to understand about like quantum. It's just like objects are just distributed, like they're just uncertain, like they don't have exact positions or exact speeds. Like it has to be, you have to look at like the relationship between the two. But okay, so Schrodinger's cat, I'm sure many people have heard of like this thought experiment. I think it's a good way to like kind of understand the behavior of atoms. Just to be clear, like a cat is like way too big of an object for this to be like real. So this is more just to like illustrate the behavior of like how weird atoms can be. But it comes from this principle of superposition, which is kind of like Heisenberg's uncertainty like leads into that. But where a quantum particle is always in a superposition of different states. So imagine like if a bunch of waves, if you add them together, it creates like another wave. So basically any quantum state can be described by the sum of like two other quantum states. So like two waves, if you add them together, they'll create one wave with like a different frequency and intensity. So it's just like that kind of idea. Um, so this equation is Schrodinger's time dependent equation or time independent equation. It's not that crucial to like understanding it, but like that's kind of um this idea of like the linear combination being like always summing to something is like reflected really well in this equation. So just like the solution to this equation is like linear. So basically any combination of like two solutions can give you like one quantum state. So if that makes sense. But getting on to the cat. So in this thought experiment, a cat, a flask of poison, and a radioactive source is like in a box, right? And this radioactive source, like it's at some point it's gonna randomly decay. Like particle decay is like a random event. So it might happen, it might not, like before or after you open the box. And basically, if the Geiger counter, that's also, I guess, inside the box in this scenario, like detects radioactivity. And a Geiger counter is like in movies, like you see those people like waving those little circular beeping things, like that's basically a Geiger counter. It has like a thin screen that like can detect the presence of radiation, basically. And but if the Geiger counter detects any radioactivity from the decay of that source, then the flask is gonna break and the cat will die. Um, and like in this scenario, like the decay from the source is like random, right? So based on this principle of superposition is saying that the cat is both alive and dead until you open the box, saying like that both states exist at once. That's kind of like the whole paradox of like Schrodinger's cat. Oops. Yeah. So to be honest, like Schrodinger's cat doesn't really have like a real defined solution. Like there's no answer to like that kind of that's like it's just like a thought experiment meant to illustrate certain like issues, I guess, aspects of quantum mechanics that we don't really understand. So the Copenhagen interpretation is an interpretation of like uncertainty that basically says, okay, the cat is just either dead or alive when the box is open. Like those are the two possible states. It's going to be one of them when you open the box. And this was originally like Schrodinger originally proposed this as like a kind of critique of it, saying like, oh, like obviously the cat can't be both alive and dead. So like that interpretation can't be right. But I'd say it's like probably the most common interpretation of it. Another interpretation is many worlds, where like when upon like a conscious mind observing the box, the universe branches into one universe where the cat is alive and the other one is dead, because it's like a random possibility. So like that's another one that people have. Transactional is way too complicated, but it basically says there's not even any superposition because waves travel back and forward in time. So everything is like distributed. Quantum Zeno is just looking at the box can like affect like the measure or affect the cat's like actual state. So those two are both like more like less well known, but like just to illustrate there's so many different interpretations of this like one thought experiment, and like we still don't really know exactly what the right answer is. But yeah, this is a really good illustration of like why quantum physics is like counterintuitive, because obviously the cat can be alive and dead, but in this situation it is. Yeah, so these are just some extra fun quantum mechanical phenomena. Tunneling. Tunneling is basically where particles are sneaking into and out of the nucleus, where normally they would be energetically not allowed. So an analogy I saw of this is like imagine a ball with like a certain amount of energy, let's say like 100 joules, rolling, and it's like has to go over this hill. And let's say this hill has like a potential energy of like 100 or 90 joules or something. So if this ball is coming in, it's obviously going to roll over the hill. So that would be like getting out of the nucleus. But in this situation, let's say the ball only has like an energy of like 50 joules and the hill is like 90 joules high. Tunneling in this situation, the ball would just find itself over the hill. Like it would suddenly appear on the other side of the hill. That's kind of like this idea of tunneling because particles are like spread out in time. Theoretically, it's possible for, one like it to like skip that. But it's kind of like I'm not sure if people have heard, but I hear people a lot being like, oh, if I stick my hand through the wall or try to stick my hand through the wall like a million times, like one time it'll go through. That's kind of this idea. Obviously, like on a big scale, it doesn't really work like that. But like tunneling like happens. It's very important to plenty of like nuclear decay processes like alpha decay. So yeah, basically a particle can sneak out even though it technically doesn't have the energy to sneak out, just because it's like distributed in space and time as a wave, because it's also a wave as well as a particle. But yeah, and then just to reiterate the fact that like quantities that are generally seen as single valued, like time, um, or like position, momentum, are actually distributed or uncertain. A kind of good thought experiment in thinking about this is that like the chance of a neutron hitting a nucleus, that's how like fission works, for example. Like you bombard a nucleus with like neutrons most likely, or protons or other particles, but it increases at lower energies. So when you slow like the neutron down relative to the nucleus, like they become bigger, right? And like it makes them more likely to interact. So that's what in nuclear reactors, like we slow neutrons down so that they interact with the nucleus. And then like fission happens, or that's how you would harness the energy from like the nucleus breaking apart. But yeah, okay. So I just threw this in here because I thought maybe some people would be interested in it because all of the recent research, or I think they won the Nobel Prize for this last year. But it's called entanglement. Einstein called this spooky action at a distance, like that, and he thought that entanglement kind of forced us to accept that our like formulation of quantum mechanics is like incomplete. But essentially, what entanglement is that a group of particles, or like let's say like two particles that were one before or whatever, separate. They can't be described independently of each other. So let's say like there's two particles that are entangled, like that's what it's called. So like when one has like spin up or something, the other one has to have spin down. Like they just can't be described independently of each other. Like they're always going to have like corresponding like opposites, like because they're together, like they make one quantum system. But it's kind of a paradox because when you observe like if you observe one of the entangled particles, let's say it's spin up, the wave function of like probability collapses. So like the other one is like spin down now. Like all the quantum information kind of disappears like once you observe it. That's like the issue that they're having with like quantum computing. There's like this idea that quantum entanglement allows you to process information faster than the speed of light, but like the result of measuring a particle's spin like in from a quantum like point of view is like random. So when you measure a particle's spin, or you want to measure a particle's spin, like you can't force it to be a certain way. Like it's going to be like a 50-50 shot of being up or down, right? And then once it's up, the other one is down, but you can't like transmit information across that, if that makes sense. And like just measuring the state like gets rid of the like quantum information. So that's like a huge issue with like qubits, which are like let's say something holds like 0 or 1. And it could be 0 or 1 before you measure it, but then you measure it and then it's either 1 or 0. It like collapses the wave function. So because now it can be both, it only can be one. So it like it just, you can't transmit information that way, or they haven't been able to figure out how to transmit information that way. But you can use it to like, I'm not really too familiar with this stuff, but you can use it to encode like, or to do like cryptography or just security stuff like that. But yeah. Yeah, so this is just like the sidebar into like what I mostly focus on, which is just like the decay of nuclei. So all those nuclei on the periodic table, and like the chart that I showed you, like that's basically atoms are turning into other atoms. So um that's kind of like the basis of nuclear engineering. We do like fission is like how you harness the power of like a nucleus breaking apart. Fusion is what the sun does. It fuses hydrogen atoms together to create energy. We don't really have those capabilities yet because it's really hard to generate enough heat to create that kind of thing. But just in the spirit, I just saw Oppenheimer yesterday, so I was gonna throw it in there just a little bit, explaining about what they're doing in that, or with nuclear bombs specifically. So both the bomb, like Fat Man, and the other bomb that they released during World War II. One of them was a gun type bomb. So basically bombarding like a mass of uranium with like neutrons and then trying to induce fission that way. And then when fission happens, basically like a nucleus, it's either like uranium or plutonium will split into a bunch of pieces. And then when it splits, it'll let go of like more neutrons which will hit other like uranium nuclei, and like that's how like that kind of bomb works. Basically, an implosion bomb is like just condensing, so eventually like it will fission if you force it really close together because like eventually something's going to hit the nucleus. And then fusion, which is like the H bomb that they're like talking about developing, which I don't think that exist. I mean, it might, but it's not supposed to. But like that's where you use a fission reaction to induce fusion, like in a bomb, and then that would have like the most devastating impact. But nothing, yeah, neither of the bombs dropped on like Hiroshima or Nagasaki were fusion bombs. But yeah, and also a really important thing I wanted to mention is that a reactor just like can't ever explode like a nuclear bomb. Like I always see like people being like really nervous about like nuclear energy because of the huge destructive power of like radioactive elements like uranium. But basically most uranium in the world is like uranium-238, and the way that we make it weapons grade is we enrich it with U-235, which is like extremely unstable, and like that's the one when it fissions it just releases like like tons and tons of energy, like kilotons of energy, like way more than TNT. And it's just like uh reactor grade materials are at a much lower enrichment. So like a reactor, like the material that you're using in it is like much less volatile basically, and it's not going to have a chain reaction. So there's just like almost no way for a reactor to explode like a nuclear bomb. Also fun fact, um the bomb tests from like just the government, like the US government, the bomb tests that they carried out, the radiation released to the atmosphere was about 10 times worse than Chernobyl. Just to like put that in perspective. But yeah. So this is just a fun thing that I found just because I'm at Berkeley, and Berkeley developed like a lot of like the nuclear bomb and discovered like 10, 15 elements on the table. So it's just like a really like cool place to be to like pursue this degree. But I found, so Glenn Seaborg, he's a Nobel Prize winner, he discovered like 10 transuranic elements, plutonium being one of them. In this picture, he's pointing to the element that's named after him, which is seaborgium, and it's actually the only element named for someone who was living at the time. And I found his like original PhD thesis like in the library at UC Berkeley, just like, and it has like hand pasted in like charts and like stuff that's like written in. So it's like this guy's actual like PhD thesis from like 1937, just like in the library. Like anyone could check it out. And what was interesting is the committee that read for his thesis, there's three Nobel Prize winners on it, like Lawrence, Lewis of like Lewis structures, if you know like electron graphs and stuff, and then Macmillan, which like nobody knows, but he also won a Nobel Prize. But yeah, I just thought that was really interesting. But yeah. Okay, so sorry, this is a bit long. On to like special relativity. Special relativity is just like when you start moving close to the speed of light, like your time and your length changes basically. And it's only really concerned with observers who are experiencing constant velocity. General relativity has to do with acceleration, but for just special relativity, like the three like main tenements are like the laws are of physics are invariant in all inertial reference frames. And an inertial reference frame is a reference frame that is not accelerating. So any non-accelerating frame moving at a constant velocity, the laws of physics are always going to be the same. The speed of light is a constant in a vacuum for all observers. So it doesn't matter like how fast you're moving, like you can never catch up to it. And Einstein formulated kind of this like thought experiment on it where he was like, if you're imagining like a wave, and for a wave to like be a wave, it has to be traveling. So if you could catch up to it, and like have a point, then it wouldn't be a wave anymore. So you can kind of think of it like that, why it's like impossible to catch up to the speed of light. Because if you could catch up, then the light wouldn't be a wave. If that makes sense to you guys. But um yeah, so it's like always the same, like you're always gonna see, like it's always gonna be C, and you can approach it, but you can never get there, basically. And then all observers agree on coincident events. So events that happen at the same place in the same time, the space-time axis, are always going to be agreed on. So the Lorentz transformations tell you what the new distance and time for objects moving at relativistic speeds are. So these are just like equations that would tell you exactly what the new times and like the new speeds are. But if you see in this picture, it's like one frame, it's like stationary, and then the second frame in red is not accelerating, is moving. So if you can kind of see like how the arrows are, like it's gonna distort it. Like imagine like moving really, really fast, like you're like if you're moving really, really fast, your length's gonna get smaller because you see like less time, if that makes any sense. But if you just look at this picture, it's just I think it makes it kind of easier to see like when you're moving like very fast, like the space and time axis gets like stretched. If that. But yeah, so basically time slows down as you approach the speed of light. This is like this graph just shows you like how hardcore the divergence at like 1, which is the speed of light, is. So basically it's like just a little change, just a little change. When you get to like 0.99, that's when it's starting to like you're gonna have crazy effects. And then at C, light is essentially 0. So that's why we say like light, like all electromagnetic radiation is moving at the speed of light, and it sees like no time and no mass, if that makes sense. So yeah. This is kind of like the most two famous like thought experiments that I guess they're not just thought experiments, they're actual experiments. But one of them is an actual experiment that explain or prove, I guess, special relativity. One of them is the twin paradox. It's not really a paradox. It's just called a paradox because relativity is like counterintuitive, but under the frame of relativity, it makes a lot of sense. But if you have a set of twins, and one of them is going away, traveling at the speed of light, and they both set their clocks to 0 when they leave, the person that comes back from space who's been moving at the speed of light is going to be younger than the person who stayed on the earth. So basically, like when you're moving at the speed of light, it's almost like your atoms are decaying slower. So time as like we view it isn't necessarily real. And also the earth is an inertial reference frame. So like the earth is moving too. So like the times that you see on earth wouldn't be the same as like on other planets necessarily. But yeah, and so in this scenario also, there's like a paradox about it because they're like, oh, if one twin is moving at the speed of light and getting somewhere, wouldn't the other twin at home, like wouldn't his clock also like run slower? But in these contexts, like only the person that's moving matters. Like if one person is like in a stationary reference frame and the other person is like moving at the speed of light, it's it's like their observations, the person that's moving, their observations are going to be the ones that like tell you where you are, because they're not going to agree at every single time. But when they come back to earth, like or when the person that's been traveling comes back to earth, like they are going to be younger and it will agree, like their clocks will agree on that, if that makes sense. But one of the experiment that was done to like kind of show this is like the Hafel-Keating experiment. So basically they took 4 clocks and flew around the world. One of them, for example, they took eastward, which is like in the direction of Earth's rotation, and one of them they took the other way, so it'd be slower. And they found that the atomic clocks actually did show different times. So that's kind of our like proof of like relativity as being real and our time not necessarily being as we perceive it. But yeah, so essentially the clock will run more slowly in a frame that isn't at rest. And then also on Earth, clocks at a higher altitude actually run a little bit faster because of the gravitational potential of the Earth. Yeah, so even on Earth, like our time is off a bit. But yeah, so general relativity, this is just a short little like explanation of it. So it has to do with people who are observers who are experiencing acceleration. It's the basis for explaining everything like black holes, quasars, pulsars. Essentially, like in this picture, like something with a huge gravity bends like the space-time curvature around it. And there's been some experiments where or calculations that where like if this is the sun, when you're trying to measure the distance, like going around it or going straight through it, like going straight through it, it would actually go like that when we're measuring it. So that's how we like know about like the curve of space-time, because you're gonna see like a different time than you'd expect. Because instead of going like this, it's gonna go like this if you send like a signal, like theoretically, like right through the sun, for example. So actually, like even small bodies of matter, like humans, like you, bend space-time slightly around them. Actually, so you bend space-time. Uh, so yeah, but just like huge gravitational bodies bend it a lot. So a black hole essentially is just a curvature of space-time. It's kind of like a cyclical concept because like the space-time curvature makes the black hole, but the black hole is the space-time curvature. So that's something that we like don't really understand that well, but general relativity just encompasses all of those kinds of things, like where that's the traditional, like if you have like a space-time axis of like this picture with the curves, like curved space, like that's kind of what general relativity is concerned with. But scientists are trying to figure out a way to reconcile the two. because things that work at like really huge gravity don't really apply to like the quantum realm. So we haven't really figured out a way to like reconcile those two. But plenty of people devote their life to this kind of stuff. So I'm sure that we will get there one day. But yeah, I mean, that's pretty much all I have. So hopefully that was followable.
That was so good, Isabella. Thank you so much. I know my mom probably has something to say. Mom, you're muted. But thank you so much. This was fascinating.
Yeah, no problem.
Yeah. I just wanted to say thank you, and you guys go ahead and start like talking and asking questions. If you have a question, yeah, go on.
Hey, thank you so much for the in-depth discussion. Well, not discussion, but information. So my question is for people who don't understand the level of depth that you're studying, what if you were to be challenged with taking your knowledge and putting that knowledge to making a positive effect on society, on the world, what kind of stuff does that information help you to try to, where would you put that knowledge, I guess, to try to make the world a better place, number one. Number two, why is it so difficult to recycle nuclear waste, which is more, you know, on your, I guess, on your degree and your studies side? Thank you.
Yeah. I mean, honestly, I feel like quantum physics isn't like super accessible for a lot of people. Like it's not really emphasized. Like you don't have to take physics in high school. Like you can never take physics. But I think it just has it's like useful to learn about, and like at least for me, it really helps me like I guess understand more like the nature of reality. Like it's taught me a lot of things about how what since what we perceive isn't even necessarily what things actually are. That's kind of like challenged me to like not try not to have like too stringent beliefs or keep a really open mind. I'd say like that's one of the things that helps me have a really open mind, I guess, if that makes sense, just because like our understanding of the universe is so incomplete. And also like the fact that like reality isn't really what you perceive it to be, considering like most atoms are empty space, like all that kind of stuff. I think it really brings in a lot of important like philosophical questions that tell you that just like it just makes you like challenge your like preconceived notions of like reality. Because I know like even talking to my parents who are my dad has a PhD in like chemical engineering, and yet he's still not necessarily like he's still like quantum like sorry. Oh, never mind. Like quantum is still like a scientifical standpoint thing for him. Like he doesn't really um like necessarily translate that into being like, oh, that totally changes like my perception of reality. It's more like, oh, it's just some science. Like that's how we describe it. So at least like that's kind of why I get really excited like telling people about it. If that makes sense. In terms of helping the world, I can't really speak for like the subject in general. I'm not sure that necessarily a greater understanding of our I don't know, like a greater understanding of our reality, or like seeing how things are like so like it's like a probability kind of makes me feel like things or like the I don't know, I guess it's like that's like a philosophical question more. And I do want to bring up more like the intersection between quantum physics and philosophy, I think is pretty strong. But like when you think about things from like that like logical scientific perspective, and then you like rationalize it or like with like how you feel and like how you understand the world like through your like emotions, like going through your life and stuff, I feel like it kind of helps like bridge that understanding, if that makes sense. In terms of nuclear waste not being recyclable, it is recyclable. I'd say we could definitely improve like processes to separate dangerous waste. I mean, there's a lot of, I mean, once a reactor like uses is like the spent fuel is like used up, it gets sent to like reprocessing facilities to make it less contaminated. That's like a whole entire industry. That's not really my specialty because I don't do a lot with like waste processing, but that's like a whole field of like nuclear engineering just dedicated to figuring out how to reprocess waste better. Obviously it's not a perfect solution. Like it is going to create like radioactive waste, whether we bury that underground or figure out how to shoot it off into space. Like there's a lot of questions that still need to be answered. But seeing what's happening with the world right now, like with the climate, like the flooding, like just all of the horrible things that are happening, I would argue that nuclear energy is probably the only possible solution. Like if you're gonna replace like oil, like wind power won't do it, solar power won't do it, unless you're in specific countries and then your geography. Like I think I'm not sure which country, maybe it's Sweden, or it was like they use a huge dam, so because they have a big river or something. So like certain areas, yes, but if people realistically aren't going to give up living the way that they are right now just to like care about climate change, so the only feasible thing that you can really do in my view is replace it with something that isn't going to cause like destruction. And when you do it right, like there's always risks with everything. The risk of nuclear power is like pretty low these days. Germany, I know they shut down all of their reactors in response to like Fukushima, but their country was almost entirely run by like nuclear power. I think France was like 80% fueled, and they never really had any issues. People take like Chernobyl and Fukushima as like really like examples of like how horrible radiation, and that's true, like they were horrible disasters. But that's why I said that thing about the like government bomb tests released more 10 times the amount of radiation that Chernobyl ever did. So like if you put it into perspective like that, I don't think the risks are too high. Reprocessing of fuel is like not too like we do keep it safe. Like yes, you can accumulate like tons of nuclear waste that's radioactive, but you bury it far enough in the ground, like nothing is gonna happen. Same thing like with like it won't be like Chernobyl, you know, if that makes sense. And I mean, we're not perfect at that yet, but with like technology like continuing to advance at it as it is, like I'm sure we'll figure it out. Because like like spent fuel, if you reprocess it, like sometimes you can use it again. So, or you can use it for other things. Weapons grade uranium is like extremely dangerous, but like we don't really make that. Or we're not supposed to in America with the treaties and all that. But I'm sure countries don't follow those guidelines. But yeah.
Thank you.
Yeah, no problem.
I have a question, not just for you, but for everyone. So recently I've been reading a lot of news, as one does when you have nothing else to do. And there recently was an article about the Anthropocene. I don't know if anyone here is familiar with it as well. I don't know how familiar you are with it. But basically, geologists and different scientists are proposing this new geological era called the Anthropocene. And a lot of them have suggested that the starting date of that era was the 1950s, 1940s, 1950s, right after nuclear weapons were tested. And the Anthropocene is basically supposed to be an era that is defined by human interaction with the world in a seemingly negative aspect, especially regarding nuclear energy and, or not energy, but nuclear bombs and the use of nuclear power. So I just think that's such an interesting topic. And like, I've seen a lot of debates about it. And I don't know if anyone has thoughts on that, Isabella, you or anybody else. But it's interesting to think about like nuclear energy as both this positive thing, as you were talking about with like helping against climate change. Sorry for those of you who don't believe it, you're wrong, but whatever. And then also causing this issue of this Anthropocene that is drastically impacting our interaction with the natural world. Anybody want to tackle that?
You said Anthropocene?
It's the Anthropocene, so it's, I'll type it out in the chat. It's like anthro, like anthropology, and then po or scene, CENE.
Oh, okay, I see. Yeah. I mean, I'll just go really quick and be like, well, nuclear weapons are horrible. Like, I don't support the use of like weapons of mass destruction in general. I'd say like I guess the technology is super fascinating. Like that's probably about it, but I don't support like the building or continuing development of like nuclear programs. The problem is like countries are still doing them. Honestly, like a country like North Korea has very limited like nuclear capabilities. Like they could only probably level maybe like a college town the size of Berkeley, like at most. So certain like many countries are like lacking in that, and I think that we should stay around there. I don't think that there needs to be any worse. Nuclear power, I don't think it's gonna like I don't really see that as like a huge issue as long as you like are reprocessing it, following every single safety guidelines. I mean, like safety for a nuclear reactor, building and designing one, super complicated process. Takes like 4 or 5 years to like even get something approved. It's just like the safeguards established by the International Energy Atomic Agency are just like crazy. And same thing with waste. Like you can't just build a nuclear reactor in like certain places. Also like certain designs, like the Chernobyl reactor was just designed extremely poorly. Like they don't make reactors like that. It had a positive coefficient of criticality, which just like doesn't happen ever. Like that's just a horrible idea. And it also didn't have a containment structure. A lot of Chernobyl would have been avoided if they just built like a concrete structure over it and they just had it like out in the open. That also comes from an age of like poor information surrounding like atomic stuff. And then I guess like, well, I'd say like Chernobyl and Fukushima are like the biggest detriment to like nuclear energy, like being accepted, I guess. So I guess I don't know. Just like I don't think it'll affect our uh natural ecosystem if it's like done correctly and every single guideline is followed. Obviously humans aren't perfect though.
Okay. I am absolutely fascinated by everything that you've said. I can grasp almost none of it, but I recognize that I don't grasp it, which I think is some sign of intelligence. I kind of am trying to I can follow. I know enough to know I don't know really what you're talking about. But one of the things you started off with the Dr. Quantum video split. I'm going to watch that, and that might answer this question because I can't quite grasp how once you observe something, it's not there anymore. Like you can't observe it because once you observe it, so I'm thinking, well, how do you measure it if you can't observe it? And I'm going to watch the video, and maybe that'll help help explain that. And then when you were talking about the waves, and you can't quite catch up to the speed of light because then it wouldn't be a wave anymore. Somewhere in my brain, I think of sound waves and sonic booms because it does seem like you can go faster than sound, maybe, and that's where the sonic boom comes from. So when you go faster than sound, do those waves not exist anymore? I don't understand. And then about black holes, I'm fascinated by black holes, absolutely fascinated by black holes. I'm always wondering, is that, I don't know, my mind goes into all kinds of things. Yes, Aaron. And when you talk about theoretically, you can't go straight through the sun, you go like this. Well, I mean, where do those theories come from? I guess there's mathematical equations behind all that, or where, how do you know you can't do this, and why do you know it goes like this? And then the last, I guess I'm trying to remember, I was just fascinated by everything you said, talking about the twins and when one goes into space and then one comes back. There's a book I read probably about 20 years ago, and Aaron, I'm going to commend this to you. It's called The Sparrow by Mary D. Russell. And in it, there is there's a colony that goes to another planet. And when I think everybody dies except for there was like a priest that went, but it was all these scientists and all, and everybody dies except for the one priest. So when he comes back, he's coming back to Earth, and he's not that much older, but everybody on Earth is quite older. And it was just a fascinating concept. But thank you so much. And I guess I'm lost in the paradox of how once you observe it, it goes away. So then how do you measure it if you can't observe it? Or how do you even know it exists if you can't observe it?
Yeah.
I don't know. Question.
I mean, that's kind of like quantum is like just counterintuitive to like what you'd think. With the whole like, I mean, wave particle duality, like how can something behave like a wave and a particle? Like, I mean, who knows? Like, but it does. And just like the experiments, I guess, are like the double slit, that Dr. Quantum video, it just sets up the experiment and shows like why we've concluded that really well. Yeah, we don't know like why that is the case, I guess. Um, I guess you make a good point about sound waves. I was like thinking about that because well, sound waves travel like at a certain speed. And then like light waves travel at c, like 3.3 times 10 to the 8th meters per second. So kind of like you can catch up to sound waves. But I guess with light, it's like light is actually made up of an electric field and a magnetic field, like moving at like perpendicular, like they're moving I don't know if that makes sense, but there's like two components of an electromagnetic field, and maybe it has something to do with like the oscillation part of it. That's how it was presented to me, at least, like, oh, like the idea like you can't catch up to it is because it wouldn't be like traveling anymore. I think sound, like the structure of a sound wave is like different than a light wave, if that would make sense. But I mean, definitely in the terms of like observation, like that's literally like the whole like paradox of, I guess, like quantum mechanics, like the fact that when you observe something, like the state changes. That video is like a little goofy, and it says like, oh, it's like the particles knew that we are watching them. Like that's how it justifies. It's from like the 80s or something. But that's how it justifies like, oh, like the behavior changing, I guess, when it observes, when you observe it. But obviously like we don't know why that happens. Yeah, I have a lot of like personal, I guess, thoughts on it, but yeah. And then the experiment about it's not an experiment, it's like a mathematical thing. I read it in a book, which I'll actually get back to the interstellar point, because the book that I read it in is called The Science of Interstellar, and it's written by the scientist that like helped put Interstellar together. So that was actually like a thought, or a mathematical thought thing that I found in his book. And it was just saying like, because you can calculate these quantities without like doing it. Like, yeah, you can't shoot a signal like through the sun, but like based on like relativity and like doing all these complex mathematical equations, like you could calculate like how far it actually travels versus like how far it should travel. And I think there's like I also think you can do a lot with computer simulations, like where you can like simulate these things with like huge gravity and stuff. So I assume that's kind of where like a lot of the or math part comes from, if that makes sense. But yeah, like quantum is just like extremely counterintuitive to like everything that you think, I guess. So like, I mean, the observable quantity thing, like I think about that all the time. Like even as like a student, I always think about how things like aren't necessarily like as we perceive them, I guess. And like that's like kind of a question that like drives my interest in the topic. Like I just love like, or I don't know, like waves, like wave particle duality is like one of the most important like things that I guess we've ever figured out about like the nature of like light. Oh, and also what has to do with the sound. I guess so the speed of light kind of sets the relationship between energy and matter, like E equals mc squared, right? And then m is mass, and then E is energy, and then the c squared is the speed of light squared. So it kind of sets the relationship between like energy and mass as a whole. So it's like a very special speed, if that may, like light is a very special type of wave, whereas like sound is like not as special, if that makes sense. But yeah.
When you mentioned that the 1980s video and the little particles are like, well, we know you're observing, and so we don't do this. It almost begs the question then, is there intelligence in these little bits of matter?
Yeah, I mean, that's the question. Like, do they know? Like, what are they made up of? Because at least like electrons are distributed just like all other particles. Like it's not a particle, like it's a wave, right? So like how would it, and it's like moving at the speed of light too, which is like kind of like the speed of light is like time defying, because like when you're moving at that speed, like your time is like 0, right? So it's like this particle, and like electrons are like there's a theory that it's like a matter wave, so it's like like it's just like oscillation, like a vibration that goes around in a circle. So it's like it's just like distributed, like it doesn't exist at a single point in space or time, if you think of it like that. Like it's spread out across space and time. So that's why it could know, because like it has already experienced time, I guess, that we haven't. If that, like, it's just like spread out. So, I mean, I don't know. Like, that's honestly like that's one of the
Okay,
questions.
so that's where I'll jump in. And first of all, hi everybody. I'm at home. So does everybody seen Interstellar? Is this am I use this as a reference point? Will it generally make sense? Because first of all, it's a mind-blowing movie. If you haven't seen it, you should watch it twice. But also, you just said a thing about like being aware of stuff and like not like, I don't know, but like the Tesseract is a concept which gets bounced around, which is a lot about the fourth dimension that I'm not even in a position to talk about intelligently, but which also, in as much as we're talking about waves and particles, and I'm already out of my league, so just correct me as I don't talk about this well or intelligently enough. But a fourth dimension would posit a situation where you could understand that in a different way. Have I
Oh yeah,
muddied the waters?
that's honestly like the perfect explanation, because if you think about it, like there's this like thought ideology or whatever it's called, where it's like if you're in a 2D world and you're square, right? Like you'll only ever see a line. Like you have no, like there's no way for that square to possibly perceive like the 2D, like that it's a square, because
Yeah.
it's in 2D world. So like that's kind of how I see like certain aspects of like quantum physics. It's like we're 3D beings. Like how could we like we lack like the ability in our brains, like fundamentally, to be able to understand like those like higher level things.
Yeah.
Like if I was a square, like I would only know that I was a line. I'd only ever see lines, and I would have no possible, like there's zero way for me to ever know that I'm actually like a square.
Yeah.
That.
I don't even know what I'm making, except that I think what everything you said today was reminding me of those elements.
Oh yeah. Frankie?
Frankie?
The real scientist?
So physics is not my thing at all, but just I have a basic understanding of the tools that we use. And as you said, just sometimes taking a measurement, looking at something in a certain way, the tools that we use can change the way those things function and behave, as you said as well. And so maybe this is something that you can do, is create new tools that help us understand these things better.
That's true. Yeah, I mean, like I kind of like my understanding of like I have lots of like ideas about like, oh, like dimensions and like things that stack on top of them. But I mean, it's a lot of it's like my own like personal like intuition and like my experience with reality as well. Like not necessarily based in like science. Like when I experience things in reality, then I tend to like go try to look at like physics and all the things that we have to describe currently like our reality to try to like justify like kind of what my subjective experience of it, if that makes sense.
Yeah,
But
and I think it's really valuable to trust your gut in certain things. If you have a feeling about something, investigate it further.
yeah, I mean that's kind of what we're like lacking. I guess like that's kind of what physics is like. Quantum physics has honestly been pretty stunted. I mean, there's been new discoveries, but the majority of things haven't changed for like 40, 50 years. Like we still use all our textbooks from like the 70s. Like it's almost like there's something missing in our like quantum mechanical interpretation. Like it's like there's some like you said with like other tools to explain these things. It's like there's something that we're like not grasping, and I would just love to like be able to figure that out, but obviously like it's complicated, but yeah, I just like there's just a lot that's missing, I guess, in our interpretation of it. Even like with like wave particle duality and stuff, like what if it was explained by something completely different? And like that's why it is the way that it is, instead of like this observation aspect. Like what if it's something that we can't like rationalize or understand on like a 3D level? But yeah. um Gabriella?
Hi, I was just going to ask a question about when you were talking about tunneling. Um, so in tunneling, do you mean like the particle will gain more energy that will allow it to like roll over the hill? Or do you mean that the particle would actually like disappear and go onto the other side and reappear, almost like it'd gone through a tunnel?
It's more like the second interpretation. Like
Okay.
the particle doesn't gain more energy. It just like it's like it has whatever 100 joules. This hill's 50 high. It just like statistically, because it's like spread out in time, there's a way for it just to appear on the other side, like tunneling, like you said, like going through a tunnel.
Yeah,
Yeah, like
thank
yeah,
you.
yeah, no problem. But yeah, I mean, actually, Interstellar. Well, I haven't finished the book I was reading yet, but the gist that I'm getting from it is that it's heavily based in real science. The Tesseract stuff is like way theoretical. Like obviously, like that's something like I don't understand. I have like a kind of understanding, or the way that I think about things is like I see like 3D, like time is maybe like 4D, and then energy is like maybe like 5D. This is just like my personal like understanding of how I see things, especially because like E equals MC squared, like the fourth dimension like bridges the gap between like the third and fifth, which would make perfect sense to me, I guess, but like that's just like my interpretation of it. But like the Tesseract stuff is way beyond me. But Interstellar, like the black hole and stuff is like based in like real science. Like basically that huge black hole in Interstellar, when they're on the planet, that's like aging them up really fast. So they made it, it's like the maximum amount of spin. Like that's like the top possible theoretical limit of like the spin of a black hole. So you can't have it spinning like faster than that, basically. And only at that really extreme condition can like where they go to the planet for like, I don't know, 10 minutes or something, and 60 years pass on the spaceship. For that kind of time dilation to be possible, the spin has to be like huge. Most black holes are not spinning like near that range of like they're spinning slower. So there still would be time dilation, but it wouldn't be as extreme as it was in Interstellar. But basically the scientists behind Interstellar, that's how Christopher Nolan wanted it to be. Like he wanted that to be the time. So he went and calculated back like what the spin of the black hole would have to be in order to like produce that. But yeah, Interstellar is honestly really great. It's like based in mostly like real stuff. Also I like it's great because it like gives like a like I guess non-science focused community kind of like a segue into like thinking about how our universe is like really like that. But Oppenheimer was great too. So I thought it was yeah, I mean it's not very sciencey though, but it is like all the science they're talking about is like legit.
I have a question, Isabella, but also before that, Jenna has tried to say something, I think, for the last 15 minutes and hasn't
Oh, I'm
gotten in.
sorry. Just you can just talk. Like I don't mind being interrupted. If I'm like honest.
Let
It's
Jenna go
okay.
first. And then
I can
pass.
wait. I can wait. That's fine. You can go ahead, Bill.
Okay. So I'm going to throw out a few wild generalizations and tell me if you think that they make sense at all. Because it's kind of the way I try to understand the history of science in the last 100 years, and particularly physics. It seems like about 100 years ago that science was basically predicated on the idea of an objective reality. And so reality is sitting out there passively waiting for us to discover it. And it has nothing to do until we discover it, but it's always there, it's stable. And what quantum physics did was blow all that out of the water, the assumption that reality is objective and that it can be, if you have the right instruments and you manage to filter yourself out of your measurements, that you'll get the real thing, right? And isn't it true that quantum physics essentially says that reality is actually in the interaction between the observer and the observed? It's not the observed itself, but it's the interaction between the two that actually constitutes reality.
Yeah, that's like that's debated. Like that's if you remember like what I was talking about with Schrodinger's cat, all those different interpretations of like what it could mean. Like the Copenhagen interpretation is like that one's the one that says, oh, like reality exists, like whether or not you like there's just like certain states that can be possible, and when you observe them, like one of them is true and the other isn't. But there's tons like because then like the many worlds interpretation is like when you observe something, the universe splits off into two universes, where one universe like the cat is dead and the other universe the cat is alive. So at least in like my understanding, I would think that that would be like another thing that we wouldn't know. Like we haven't really decided, because observation, like measuring something, definitely affects like the state of it. But it's like who's to say that it's the act of measuring that does that, or more it's like, or could it be like, you know, our perception of reality or our understanding of like wherever we are in our like dimensional universe is like too lacking for us to be able to comprehend something that's like not just one thing, if that makes sense. Like but like that's debate, I guess. Like that's debated. Like there's tons of interpretations into that, like quantum Zeno, and like that's I think it's also called like the Turing paradox. That has more to do with like the observer like being able to affect reality directly. So there's like quite a few, like if I would like I'm not too familiar with like all the interpretations. I really just focus on like the first, like many worlds, and like Copenhagen is like pretty much all that's necessary for my understanding at least. But there's like many different like ways of thinking about whether or not like it is truly observation that is like collapsing the wave function, or is it like the wave function collapsing itself because of our us, like if that makes sense. But yeah, I hope that answered your.
Yeah, could you also talk about randomness? I think because it seems like that's one of the reasons that quantum theory was resisted at first, and
Yeah,
even
yeah.
Einstein was very resistant to it, and he supposedly said God doesn't play dice with the universe.
Yeah. Yeah. I mean, God seems to actually play dice with the universe, even though Einstein said that. But I guess like the nature of like particle decay, like all like nuclear decays, like those are all random. Like they have a probability of occurrence, but it's like it is a probability, if that makes sense. Same thing with like the idea of an electron being distributed. Like it has a probability of being in a certain place at once. And like that's the randomness element of it. Whether or not like the universe is like truly random, like if there's like order to the randomness, like I wouldn't know. If I knew, then I would be famous. But yeah, just like if there's like order to like the random occurrences that happen, like that, I feel like that could be true. Like there is a greater order potentially that we aren't necessarily aware of, but at least like the probability of where things are. I saw it like presented like this once. If you have a big infinity, let's say like 0 to 100, like and like that's and like all the numbers between 0 to 100, which is infinity, right? And then you have like 0 to 10, all the numbers between 0 to 10, which is also infinity, but it's a smaller infinity. So if you think of it kind of like that, it's like the probability is smaller, even though it's like in another infinity for like people or whatever, versus like the grand, like there is a bigger infinity, but like you would be in like the smaller infinity in terms of like probability. Like it is still a probability of like literally infinity, but it's like a more constrained probability. It's like a smaller infinity, if that makes sense. Did that answer?
Yes, yeah, it makes sense. Thank you.
Okay, yeah, no problem. I read that. I read that in an article somewhere. Sometimes like if you have like these questions, sometimes like if you just like Google like these like thought like like things on the internet, like there's so much information, like there's so many resources of like all of these different interpretations, because people have so many different opinions and like interpretations of like what is reality, like what is quantum. And it's just like I kind of like to read a lot of different ones and kind of pull from which ones I think are like the most make the most sense to me. But I also think there's like a lot of different ways to think about something and have like all these conflicting things, or like have all these like different interpretations be true at the same time, if that makes sense. But yeah, that's one of my favorite things to do. But yeah.
Yeah. Jenna, did you have a question? Jenna was first.
My question, I don't know. It might open a can of worms, or it might be out there. I'm just fascinated by the link between the human mind and physics with respect to the possibility that like the power of the mind, or that thoughts are energy, or that we can potentially exist in a past, present, future state, or even with respect to spirituality and all of the different interpretations, and how because you talk a lot about observation, and obviously our mind is limited in what it can understand. And so just toying with the idea that we haven't tapped into the full potential of our mind, therefore we haven't tapped into fully understanding the universe. So I don't know, it might be really out there, but I'm just fascinated by the possibility of those connections.
I mean,
that would give some explanation of our human existence.
I mean, like I have a lot of like my own personal like thoughts on that. I wouldn't say they're based in like science. Like just a lot of or certain things that I think at least with like quantum physics, like quantum physics really tells you that everything is energy. So I feel like that really correlates to like, oh, like your thoughts are energy, like all that kind of stuff. And the fact that like I always like to tell people that like, I mean, everybody has an infrared field around them, and that's like heat, but it's also electromagnetic energy. So like those particles like are moving at relativistic speeds. So it's almost like you have like a time-defined field around you. And at least like in my mind, I mean, this is like just like me personally. In my mind, I would think that like things like intuition, where you like know how you feel about something before it happens necessarily, if those like if your emotions were described by like waves, that would make the most sense, like vibrational energy, because then those waves are distributed across time and space. So if you have like a bad feeling about someone that's like unexplainable to you, since like if emotions are like waves, corresponding to that emotion, like it would be distributed in time and space. So it would make sense for like if you're able to access it, it would make sense for like you to be right in that feeling. Like if you're right. Obviously, if you're wrong, it's different. But if you're right, like to me at least that would make sense. Like the concept of like intuition. But yeah, I'd say like quantum physics is like highly connected to like spirituality, just because it just like everything you're looking at doesn't like that's not what it looks like empty, like the fact that most things are empty space, like kind of um like that kind of pushes more towards the interpretation that everything is like vibrations and energy, which is like much like a much more spiritual like viewpoint of that, I guess. But yeah, no, I mean like I think about that stuff all the time. Like a lot of like my interest in like quantum physics is like has to do with trying to like understand like my subjective experiences. I just happen to be nuclear engineering. Nuclear engineering is not is not really quantum physics. It's it is. I guess it uses a lot of like principles of quantum physics, like important parts, like uncertainty, like probabilities of decay and stuff. But it's not about like it's just like the closest engineering major I could have possibly gotten to like actual physics. Um, but yeah, I just like that's my like my interest in the topic comes from like those kinds of interpretations and like the way that I just like view reality and stuff like that. Or the way that I feel, like if you consider yourself like an empath or whatever, like those feelings, like having those feelings of like knowing how someone feels aren't necessarily like explainable by like science. But in my head, like quantum physics would be the way to explain that. Because like if emotions are waves, it would make perfect like waves constructively and destructively interfering with each other. That would kind of make sense. Like vibes, like people talk about. But I mean, yeah, that's like a very like spiritual interpretation. There's tons of work on this. When I was like little, like 18 or something, I'd be like, oh my God, I wonder if anybody's ever thought of this before. But there's actually tons of like writers and like stuff who like try to explain like quantum physics from like a spiritual standpoint. It's just like it's very theoretical. Like obviously you can do a lot of experiments in that kind of stuff, but maybe one day. I have like random ideas. Well, I mean, the science behind them is lacking, but I have like random ideas where I'd be like, oh, this is how you can test someone's like emotional response. Like, can you measure it? Like, can you measure like their heat signature or whatever? Is it going to change? All these like little things that theory or experimentally haven't really been explored yet. So it's still like very much in the theory process. But I think there's definitely like a bigger wave of that coming. If that makes sense.
Pardon me, you guys, I have to interrupt for a second. We have some folks here from England, and it's really late there. It's like midnight, right, guys? And we usually do 2 hours, but we have a queue. We have 2 more people. John's next, Deborah, and I think a few more people have raised their hands. Only usually go 2 hours, but I think under the circumstances, it's fascinating, and I think everyone's really enjoying it. So I want to continue, but I wanted to stop. So in case anyone had to leave, I wanted to just acknowledge that it's been fabulous, and we're going to keep going. But if you guys from England need to go, I totally understand. I'm so glad you came. Yes.
I do want to
Sorry.
just say, since people are leaving, our next Shine on Salon, I'm going to announce this
Yes.
now, is going to be
Yes.
tea.
Where
Tea,
am
will you
I?
wave?
Yes, right here.
And I September what, 29th or 30th? It's at the end of the month of September. But T, would you like to just give like a 30-second little blurb?
And by the way, T's a chef, so go.
Wow, way to give it away, Alicia. I'm gonna do the impact of like the African diaspora on Southern cooking, and do a little side by side of like a Ghanaian dish, which my family's from Ghana, and how it's how there's like Cajun and like Southern dishes that have come from those meals that I grew up on.
Now, T, didn't you say we're gonna get to, if we want to, buy the ingredients and cook along with you kind of thing?
Yeah, so I'll be talking and cooking because I'm not very good at just speaking without doing anything else. So if you'd like to follow along, you definitely can. I could send out like maybe to Juliet like a short ingredient list. And
please.
yeah, I'll drop some tips and tricks that I've gained along the years and stuff. Yeah.
Yeah, so just so that does mean please keep an eye out on our social media. If you're not following us, follow us. It's Shine on Salon. There might be dots in there. I don't know. I'll send a follow-up email, and then check your email because that's where we will get all of those ingredients, all of that information to you, and spread the word. We might not do a live one for that one since it will be cooking based probably, but yeah, look forward to that.
So we'll continue, just in case you guys, Fiona, all you guys, thank you for coming from England. Really appreciated it. And we'll just keep going. So John, you're next, and then Deborah, and we've still got a queue. So
yeah, thank you, Alicia. We probably will go in a second.
bye, Fiona. Bye, sweetie. Love you guys.
Thank you for coming.
Thank you.
There. Okay. I just wanted to encourage everybody to track some of the findings with the James Webb Telescope. They're doing some observations that are having a huge impact. I think they're going to make us unlearn a lot of this stuff. They're basically saying that the observations disprove the Big Bang theory, and so bring into question a lot of the theory of relativity. And you know, the one thing that the theory of relativity and quantum theory share is that time is a dimension, and that's basically what the telescope now can look into deep space, and they see that these galaxies haven't really changed, and so the theories we've been operating on are basically being disproved. So we're in an exciting time.
I wouldn't
implications that's going to happen.
I wouldn't necessarily say disproved. I would think more maybe present an alternate explanation. I don't think, well, currently the telescope has not yet disproved the Big Bang. And like the Big Bang is still one of our like most fundamental things for like maybe understanding how the universe was made. But it's not necessarily like it's already not like our only interpretation. Like there's no like we don't prove the Big Bang either. I guess. So let me try to think about like the Big Bang theory is already like disputed, like string theory, like all these other theories like come in to like try to explain it. And quantum physics, I mean, it's always evolving and changing. And at most it can be like an approximation of like what we know. Like there's always going to be like new things like coming in. I wouldn't necessarily say like disprove is the right word. It's more like new information gets learned and things get altered and shifted a little bit. But a lot of like the fundamentals, like Heisenberg uncertainty, like the idea of like superposition, like I don't think that kind of stuff is going to get resolved for quite a while because like it's just not on the scale of like our human comprehension. But as of now, like the telescope has not disproved The Big Bang Theory. I've heard that's like a pseudo story that's been spread around, actually. So I wouldn't read too much into that part, but just definitely like, I mean, everything I'm saying now in like 25, 30 years could be totally shifted. It's just like this is at best our most current understanding of like what we know. And relativity is always changing. Like there's so many different interpretations of like how people think it is. Just like the immutable laws about like how the laws of physics are the same in every like inertial time period and how like time dilation occurs. Like those are pretty like immutable, I'd say, at least in these days. But
Okay. Hi. First of all, thank you and good luck with your studies. It's very exciting to be passionate about something and see where it goes. So that's fantastic. Let's see if I can get out my thoughts clearly. Piggyback on something you said earlier, the connection and your interest of philosophy. And then is it Jenna? Going there, right? So I've been going there too. And I was like, okay. And then just a fun fact, I was saying to my friend Kirsten before, I'm related to a famous theoretical physicist. So that's just kind of cool. His name's Martin Rochek. He's a professor at Stony Brook and helped write a book with Isaac Asimov. So I always tease that I'm like, you know, a couple genes away from being really smart, but like not really. Anyway, so I've been a practicing yogi for several decades, and that includes meditation. Of recent, I've been working on a pretty deep certification, so I've been spending a maximum amount of time kind of every day concentrating sort of as a student again. And I don't even know your name. Amy, when you were talking about the observer, it's like that word kept coming into my head. And then it really started to make me think about in meditation, whether you've meditated or not, there's these different fields, right? There's like in a simplistic state, like right now we're in a waking state, but then we could be in a dream state, we're sleeping, but it's still us. It's kind of like the cat, right? It's like, it's still us, but we're asleep, but we're not fully conscious. And then there's like a transcendent state and a cosmic state and a state of divinity where it's like, there's no separation, right? So, and then several other states. So I kept thinking, if that vastness is so hard to explain, I mean, just being a human and trying to understand ourselves and our thoughts and all of that, what if in the human form, the observer is the ego? So it's like in Aaron, you're pointing, something, yeah, laugh at. It's making sense, maybe. Wait, maybe
No. Juliet just sneezed. It's fine.
Oh, okay, good. I was like, maybe I'm making sense, maybe I'm not. So in meditation, it's like you're a watcher of your thoughts, right? So it's like you're present, but you're like in another sphere of yourself. And it's only when the ego comes in that you're an observer of these experiences. So it's like, well, then why wouldn't that be a bigger thing? Kind of like your description just now of like the 0 to 100. It's like the 0 to 10, like maybe we're just like a 0 to 1 or like a 0 to 0.1 or something. It's like it kind of, for me, I don't understand the math of what you're saying necessarily, sort of the hybrid concepts, but through my lens, I was like, this is what I kept thinking about. And then just maybe one other thought, you brought up emotion. So, and I'm working with the Chopra Institute in California. So, you know, some people might be familiar with their deep work, and Dr. Sheila Patel, who's a doctor on their staff and also a Western doctor, in a Q&A session I was in the other day, somebody asked about the difference between emotions and feelings, right? And so she described, so emotions are like what you experience as a story connected to something in your life, past, present, future. And the feeling is that intellectual or that intuitive experience that you're having. So I'm like, okay, well, if my mind, I'm right here in this room in the Lavell's house, but like if my mind goes to a past thought, I'm going to have an emotion of this. So it's like it made me think I'm in my own little universe, that we're all in our own universe. Anyway, it was more an observing thought. Don't really think there's a question in there, but I appreciated that that was just brought up, and I thought, okay, I'm not alone also in thinking that there's definitely a connection there. So that's all, and thank you.
Thank you. That was super insightful. I mean, especially just like when it comes to the ego, like I've always thought that like outside of like our human brains, like the ego doesn't really exist because it's like a product of our brain. I don't know. My science on that is like lacking, so don't quote me on that. But like without the ego, like you don't have like like you don't have like an like you don't have a self, like an individual self, I guess. So like I definitely really like hear what you're saying, and like that was just great. Thanks. But yeah,
Thank you for also making me not feel like I'm alone.
Can I even explore that thought with y'all? Because this is just occurring to me as we kind of talk about it. But I was thinking about the Tesseract before, which is a moment. Well, no, it's what do you want me to say? It's a thing, but it's a place where you can look in on a thing that isn't where you are or even when you are. And the ego is somewhat, or no, the ego is like the time and the place. And the ability to disconnect or to look in on yourself in a thoughtful, without being judgmental kind of way is a similar personal experience. I don't know what I'm saying. I really should stop, but I'll keep going. So, because I just am curious what everybody would think about when you look in on yourself and what that means in that kind of gut or emotional sense, which, the ego or whatever sense of identity we have affects thoughts. So that is not necessarily reality. It's just our experience of reality. And I sort of think one of the things Isabella said that I really liked the most was how it's our experience or any observable. Oh, you said it so much better. I wish I could look at the slide again. It doesn't matter. That you don't know until you look at it that that's what it is. And then you force it to be. Do you say, Isabella, is that kind of what you're sort of, I'm quoting you, so I don't want to misquote you.
like when I was talking about the entanglement stuff, like the act of just like observing the state like fundamentally changes it, and you can't like force it to be like a certain measurement. Like it's going to be random. Like when you look at it, it's going to be 50-50, it's going to be up or down, and like that's
it's going to be random, but only when you look at it. And until then it was something else that wasn't really either. That is an interesting thing for us to all to just think about in our experience. And Sophia, go.
Wait, sorry, Sophia, we had a little bit of a cue before you. Bill,
she's on his comment. Sorry, I just got going.
As long as Bill gets a chance in just a second, he's been waiting patiently. Thank you, guys.
Oh, you want me?
Yeah, go. I'm trying to let everyone go in turn. I know you've been waiting a while.
Oh, no, I just want to go back to something more simple in nuclear engineering. Like, I'd like to know your thoughts on commercialized cold fusion and when we can expect to see that.
Well, I actually do not know that much about it. I'm actually taking a class on fusion this semester, actually. So I don't really know too much about cold fusion. At least like my understanding is like fusion. Yeah, I really don't know too much about that, because like fusion is just like you just need a massive amount of energy to like slam two particles together so that they fuse. I don't really know the science between how it would be cold. Maybe you slow it down enough. But fusion is like super emphasized as like how people are doing research on it. I mean, like even at Berkeley, like there's only one class on like fusion. Like the class, and like there's not like it's not like a huge core. Like we mostly focus on fission, but there's tons of theoretical research going in on that. So honestly, I'm sure it won't be long, because like we've achieved like fusion in like certain states, I think, already. But yeah, I actually do not know too much about fusion, other than that's what the sun does. But
No byproducts, no waste products.
oh yeah, I guess that would be true. And also it'd be more energy, just way more energy than fission. Fission's already a huge amount of energy, but fusion's like even more. I mean, like fusion powers the sun for like billions of years. So if you think of it like that, like if we could harness the power of like fusion, then like the world would probably like that's like unlimited energy basically. In our like view, it's like a free energy source. So that would like solve a lot of issues in society. Brought about by
You'd have the answer.
yeah, no, I don't have the answer, unfortunately. Yeah. I would say though, like the next 50 years are gonna be super instrumental for like fusion stuff, because like now that we know so much, like there's not too much left. Like we've already discovered pretty much all the elements. No more elements left to discover. All they do to discover elements is just like take the bigger and bigger ones, which are super unstable and only last like a few milliseconds. Like all those big elements on the periodic table are super unstable. Like they literally decay in like a tenth of a second. And just shoot things at them and hope that they stick, and then that creates a new element. So I think we're done there. So now that there's no more elements to be named, yeah, I'm not sure how cold fusion works. I only know how like hot fusion.
Frankie, do you know? The other scientist in the room? Frankie?
No, sorry. Like I said, I'm a biologist, not a physicist.
I
But
guess. Well, sorry.
Go ahead, Isabel.
Just reading about it, it says there's no accepted theoretical model that would allow cold fusion to occur. So we're probably even farther behind that, because there was only one experiment where they said that like I don't know, like it's just like the experiment they had wasn't able to be replicated. So more like it's likely it's a statistical fluke than like actually cold fusion, but just reading about it. But it's still heavily, I guess there's still like a lot of interest in it. But honestly, I would think that like heat fusion, like fusion from like heat would be more likely to happen first in a controlled setting. The problem is like we can't control it. But in a controlled setting, I'd say that would be more likely than cold fusion, at least with the current state. From my very brief understanding of reading about cold fusion for like 1 minute.
I should have said commercialized rather than cold.
Oh, commercialized. Yeah.
Cold is not correct. That's just less heat.
Yeah. Commercialized fusion, maybe. I mean, if we just find a way to contain it, I guess it's just the conditions, like you have to have like the sun. Like those are the kind of conditions you need to create fusion. I mean in H-bomb, it's fission induces the fusion. So that's like that. And I think H-bomb is like a real I'm not sure if they built any because that's like classified probably. But but yeah, I don't think it's unable to be a reality.
Sophia, you've been waiting to go.
Oh, that's Sophia.
Thank you. Actually, T's been waiting impatiently. So
I've been patient. Hey, so when you're on the Lorentz transformation thing, it reminded me of like this, I think it was an article, or honestly probably something I saw on Twitter, so I don't know how, accurate it is, but it was like, it said that when you're running, like when it's raining, and you run, you actually get more wet than if you just walk. So like, even though you're in the rain for a shorter amount of time, because you're running, you get more wet, but if you were just to walk, you'd be less wet. So is that true? One. And two, I need to know if I gotta run in the rain, like.
That's true. I mean, operating from the basis that it is true, then I would think that like when you run, well, okay, when you run, you're not going to hit relativistic speeds. Like Lorentz, for Lorentz transformations to be like legit, you have to be going like something like close to the speed of light, or like even like 0.6 times the speed of light is still like very fast. So so if you were running, I would think that would be because like the raindrops would see more area. Because it's like, when you slow things down, they become bigger. I mean, that would be counterintuitive to what you're saying, because when you speed things up, like you should do less. But yeah, I'm not.
I know this one. Yeah, so when you're running, you get more wet because more of you gets wet, because the front of you gets more wet, because as you're going, like more will hit. If you're thinking of raindrops coming straight down, no wind, right? Instead of just hitting your head, now they're gonna hit your whole body, like the whole front. So then when you wring out how much water is in someone, they'll be more wet because it'll have hit more.
Oh, like EMC squared, the math of your body. Yeah. Boom.
So basically,
I also was very interested in should I run or walk, and I still run. Even though I'm getting more wet. My head doesn't get as
What
wet.
if you have an umbrella?
a pencil. Exactly.
Well, T also played D1 soccer, so she probably runs at the speed of light, which means time is slowing down, which means she's getting more rain.
Which means she's aging slower. The atoms are decaying slower when she runs that fast.
That's why no one takes her ID anywhere.
Yeah, I do run at the speed of light, so this was probably just an individual question, sorry.
Don't run, you might slip and fall.
I have a quick question. Julia, the thing that you were asking about, I was wanting to ask Frankie her opinion as a scientist who's been, in the field a lot longer. Did you have any thoughts on when Juliet was talking about
Anthropocene.
yes.
Say it again.
Say it again, the word
The Anthropocene.
Anthropocene.
Oh, yes, I've heard about it. Do I have any thoughts on it?
Yes.
Oh my gosh, so many.
I mean, I just wanted if you would share scientist your opinion as well, please.
Oh, well, no, it totally makes sense. And I think humans are horrible. And yeah, that's kind of the gist of it. We've done this to ourselves. One of the greatest ironic things I've heard lately was someone thanking the inventor of the air conditioner so that they could exist in the temperatures that we're going through right now. Well, if we hadn't used that energy to run all air conditioners, we wouldn't have had to worry about this global change, and we wouldn't be living in places where we shouldn't be living. So you think about cars and air conditioning and a lot of other things, plastics. Granted, I wouldn't be here if it weren't for plastics. So if you have any medical issues, you wouldn't be here. I don't really know much more about it other than that, even though I studied genetics. I haven't really looked into it just because it just sounds so depressing that we've done all of these things to ourselves. And an additional irony is that a lot of us who grew up or had parents during that time, at the beginning of that time, in the 70s, we were looking for all these ways to help the environment, and we've just epically failed.
Green.
Yeah. Sorry, so I have nothing heartwarming to say about it.
You have something to say? You just wrote something to everyone about it.
I was recommended.
Y'all's camera is off, just so you know.
No.
Oh, sorry.
It's okay. We turned it.
Talking, we'll get it fixed. Sorry.
But also, while you're, oh, sorry, Isabella.
Oh, this is just a random remark on that, but this class that was called like climate change mitigation, like within the last year, it got renamed to like climate change, like what's the word? Like not, or maybe it was from prevention to mitigation.
Yeah,
exactly.
They changed the whole name of the course now.
Yeah, we're almost in such a spiraling trend that the question is prevention. I don't think there's anything we can do at this point, but I don't know. Again, that's not my area of expertise.
Thank you.
I'll be the naive optimist and merely posit that air conditioning did create the problem, but also solved its problem, or at least I wouldn't say solved it, but maybe created a bridge into a world where I'm not defending air conditioning. I'm not, just hear me out on this, but that in as much, let me zoom out, that the Anthropocene era could be marked by the question, humans have created a world where they may have increased difficulty surviving, but also have increased their ability to survive it. I don't know that that's a hopeful thing, but it does suggest that it was never in our genetic construct or anything to wow, I'm really derailing this. I'm just going to be careful, so shut me up if I go off. But if there is a problem, I'll solve it. Check out the beat while the DJ revolves it. And it's really all to say that sometimes problems come to our light at the exact moment that we're in a position, and I won't say ability or willingness, sadly, to solve them. But we're in a world where, in spite of the crises that we're facing, we're also in a realm where more intelligent people are more connected with more resources, should be able to confront those than ever before. And the only thing stopping, wow, this is really going to go dark. I got to be careful. The only thing stopping us is ourselves and perhaps our government. That if we reach out, there are intelligent people with solutions. Cold fusion is one of them. Cheap renewable energy. Juliet, go.
Right. I think it's just, we're definitely getting off the general topic of nuclear stuff. Not a problem. But yeah, I mean, I think the thing that's alarming in my perspective, especially like now that I'm living in a space that is one of the most natural spaces you can be in the United States and the world. I mean, it's something where, like, yes, there are things we can do as a world to combat climate change, to combat all of these issues that have been created by ourselves. But the reality is the majority of people don't either care, believe it, or don't have the money to fix it. Because, like, I can spend all the time I want recycling, which recycling is a scam, by the way. If you didn't know that, plastic recycling is a scam. But like, I can spend all my efforts doing XYZ, and like, yeah, for me personally, it's benefiting my life. And I'm not saying you shouldn't do it, because the individual matters if all individuals did it, it mattered. But like, when you have people like Elon Musk and what's that guy's name, the Zuckerberg dude who just built like a fucking octagonal thing in his yard, like, that's the problem. It's not the individual, it's the higher ups who have the power to do things, and they're just not. But I actually have a different question, going to change the topic slightly for Isabella, because we've had this conversation before and I still find it fascinating. And I don't remember who spoke about the yogi in the room. I don't remember your name. I'm so sorry. Deborah? Perfect. Yeah. I thought you should talk about, like, sorry, kind of loud out here, energy and crystals. Because, like, I know we spoke about this individually at one point, but like, just talk about that. I'm not gonna even try to explain it myself because I don't know.
I mean, I just have this idea of like, so like crystals, right? Like, there's lots of like crystal girls, like, oh, they're like this crystal will give you this kind of feeling, like all that kind of stuff. Thinking about it from like, I have a lot of crystals because like they're pretty, and it's like more about the mental thing rather than the actual energetic component of it anyway. But like, just like crystals, like, they're perfect crystal structures, right? So when a crystal, let's say it's like a perfect black body emitter, which is like just like a black object that will absorb all radiation and release like the same amount of radiation that it absorbs. And radiation is just like energy, by the way, like in this context. But let's say like a crystal, it has like a certain crystal structure. It's a perfect crystal. Like all of the atoms are organized exactly the same. It takes in some energy. The electrons inside the crystal get excited. They go up in orbital, right? Now, when they're releasing that energy like back out into the environment, like because it's a perfect crystal, right? So when it takes in energy, the electrons getting excited, all the electrons are like getting excited kind of like the same amount because it's all quantized, right? It has to be at a specific energy. Only specific energies are possible. So when it's releasing that energy, it's releasing a gamma ray that's like of a certain frequency, like of a certain wavelength, always, right? So it's like absorbing energy, all the electrons get excited. Maybe some get more excited, so there's like several possibilities of energy. But let's just say like they all get excited, all these individual electrons attach these atoms, and then and then it releases it, like releases the energy in the form of a gamma ray, and that's like a wave, right? So a crystal, like when it takes in energy, it's like transmuting that energy into like a different frequency and like a different like specific wavelength. And like wavelengths are like how we get like colors, like stuff like that. So let's say it's like infrared, like it's gonna emit like specific infrared wavelengths. And maybe those wavelengths correspond to different things like emotions or whatever. It'd be like on a small scale, but like that's why I like the idea of like crystals because it's a perfect crystal structure. Like when it takes in energy, it's gonna emit energy at a charistic frequency, a charistic wavelength. And it's a perfect structure, so it's like it's always gonna be the same. Like it's always gonna be releasing the same exact like type of energy. I mean, I think it's possible that there's like because electrons can get excited like more, so there's like a few different types. But like at the baseline, like the first excitation level, which is like the most common, it's gonna like there's a bunch of waves of like a certain frequency and a certain length or wavelength that are getting like emitted by that. So I just think that's like a fun, or that's how I've like rationalized crystals to myself. But yeah. And I mean, I guess it does make sense how like from an atomic standpoint, because whatever's like emitted, like when something absorbs energy, it's gonna emit it. So since it's a crystal, it's gonna emit it perfectly in perfect frequencies and waves. Well, not completely perfect, depending on the crystal, but yeah.
Just a quick question, just because you know about crystals and the structure and all. So white, right, is all colored.
Yeah.
Correct?
Yes.
So then all those waves are becoming one wave?
Yes, but in this context, it's not visible light, which gives you the color. It would be like a different, like maybe like infrared, or like which has like its own rainbow, but we can't see it because our like eyes are only primed for infrared. So like in this context, it wouldn't be like colors that you're looking at. I'm sure the colors probably affect like the crystal structure, like it has a certain color probably because of like some intrinsic elements like inside of it. So that's probably where the color comes from. But I would think that like in this scenario, it's like let's say it's absorbing heat energy and it's like re-emitting heat energy. So it's not necessarily color, but heat, like infrared, like there is like a rainbow. We just can't see it. Like, oh, for context, like humans, like the electromagnetic spectrum is like if it's like this big, humans can see like this much of it. And then like bees, if you ever like Google how does a bee see, like it's like slightly down. It's like 100 or 200 nanometers shifted from our vision. And like because they see like UV and stuff, and it's totally different. Like the colors they see, like the way they see reality, like see all the UV patterns on flowers and stuff. So it's like only a very tiny sliver of reality that we can even like get to experience. Just because our brains or like our bodies choose this wavelength, I guess, to see. But yeah, in this context, it wouldn't be like light. It would be like other kinds of electromagnetic radiation. Most likely infrared, which is like heat. In terms of like crystals. But yeah, basically it's like this is a nucleus, there's like electrons. This is a perfect crystal, right? So it's like they're all exactly the same, organized. When energy comes in, this electron like comes up an orbital, like it just like shoots up, and then when it goes back down to like the normal orbital, like that, like how when it goes back down, like that distance, or I guess that energy it goes back down is quantized, so it can only be certain numbers, and it would always be like the same number for the same atom, if that makes sense. For that one orbital, it could jump up like 2 if it got more energy. But yeah.
Isabella, I actually have a question. So don't laugh at me. What about the future of the possibility of time travel?
Oh, I mean, that's like that's like highly like, I don't know, like the main consensus from that idea is like in black holes. Like if you imagine, okay, the structure of a black hole is like it has a singularity at the center. No one knows what the singularity like is, but basically like it curves space-time around it and goes to this like super dense point. And when you're going into the black hole, like your time essentially is slowing down as you're like moving into there and going one direction. Like time is moving forward when you're going in, so like time can only move forward as you're approaching the singularity. And there's this concept of like wormholes, where it's like, oh, when you go through a black hole, let's say there's another one on the other side, if you're going through and your time has to like be moving forward, and you could pass through it, hit the other one, which is like inverted, right? So now you're moving out of it, then your time has to be going backwards, because time is always going towards the singularity or moving forward towards the singularity. So that's kind of like the only thing we see, like the idea of like, oh, if you go through a wormhole, will it put you at a different point in the space-time axis? I would think that, sure. I don't think a human could ever survive something like that, because like who knows what's in there. They suck in light too. Like black holes don't even let any light in. So also a fun thing about black holes is like if you're an external observer and you're on the edge of the black hole. Okay, there's somebody that's on the edge of the black hole and you're the external observer. That person, when they fall into the black hole, in their perspective, they're gonna fall in. But in your perspective, you're the external observer, you'll see them hover at the edge forever.
Wow.
Like,
That's
so
cool.
like black holes are just like curvatures of space-time. Like it's like curve, like the hardcore gravity, like the curve of the black hole, like that's the space-time curvature is the black hole, but the black hole creates it. So like that's the only like idea of like time. If time travel was anywhere, it would be like in the side of black hole. But we don't really know what's inside. Like we don't even know what the singularity is. Other than it's just like the like dense core of like the black hole. But
thank you.
Hopefully that makes sense.
Fascinating. Anyone have questions, you guys? Anyone else?
You should all watch Interstellar after this.
Oh yeah.
Okay, and read the book that Laura recommended. We'll put this on the website.
And was that the Anthropocene or the other one?
Anthropocene review.
Yeah,
that's what.
Oh, this book. If you like black holes.
Yeah.
Yeah, if you like black holes, if you want to learn, I'd say this book is pretty technically challenging. So it's not the easiest like fun thing. But if you want to learn, like this book does a great, and it also pushes like all the theory. Sorry.
How about this? If you guys have recommendations to send out, either text them or email them to me, and I'll include them in the email to follow. So that way, if we are interested in reading or continuing this conversation, you'll have access to those.
Isabella, everyone I think can agree. I mean, it was a fabulous presentation. That's the longest we've ever gone. I mean, wow.
Thank you. I hope it was like
You beat Bill, which means there's proof that time travel exists.
Hey, And T, we're so excited about your
Where did
in
you get that?
September cooking class.